Let's start with a summary of what we remember about quantum mechanics. Now, so far we've only really discussed one of the postulates of quantum mechanics, and that is that everything in the universe can be described by an element of a Hilbert space. Now, what is this Hilbert space? This is a vector space with complex scalars and an inner product. Now, our vector space means that anything can be in a superposition, and the best description of that, or any particular vector space, is its set of basis vectors, in which case any state can be written as a linear superposition of those basis vectors. And the inner product is how you turn two of those things into a complex number. It's linear, it's complex valued. We discussed turning vectors into covectors by taking the Hermitian conjugate, and we have basic properties of the inner product that it gives us a norm. One of the most common things that we want to do in quantum mechanics is change basis, because often we can write our state down in one basis, or we can write some operator down in that basis, and it's very simple. But in fact, in order to relate it to some other operator or some other state, we need to be able to change basis. And the easiest way to do that is with something called the completeness relation. A proof of the completeness relation is actually part of the assignment. And what it says is that if you have an orthonormal set of basis vectors and you sum up these are called the projectors, so when you have the ket and then the bra, then that's called a projector for that state. And if you sum up all the projectors, then you get the identity. It's called the completeness relation because you can imagine if you miss out on some of these, then you're going to have some sort of holes in your identity here. And so the idea that this set is complete is bound up in that you've got all of them, so you get the full identity. Now, so you're going to prove that. In a continuous limit, it looks like this. Or indeed, if you have a mixture of discrete and continuous indices, then you simply have to sum or integrate over all of them, and you get the identity. And this is a very powerful way to change basis, or put something in a basis, and we'll explain that by an example. Supposing you start off and you've got some basis V. So that's a orthonormal basis. Then a completely general state can be written like this. Supposing you know about some other complete orthonormal basis, the U, what am I going to do? Well, what you can do is you can apply the completeness relation using either the U's or the V's on your state. If I apply it on this state here, then because everything is linear, I can take these sums out. I can take this complex number out. And then I've got an inner product between UK and VJ. And of course, that's just a complex number. So these things here are just sums of complex numbers. So this thing inside the bracket is just a complex number that depends on K. And so this is the coefficient in the UK basis. So I've changed basis. All I need to know is how the two bases are related. I could have started from here and simply applied the completeness relationship directly. And I would have seen from this inner product here that I'd put it in a basis. So this CK is defined as this complex number here. So that's how you change things from states from one basis to another. Now I want you to have a go by yourself at expressing the operator X in one of these two bases. Try that cold.